In today's lesson, we're going to be looking at solving exponential and logarithmic equations. So taking a look here at our first example here, we have an exponential equation. Again, you can see that here. These are written exponent form. This is your base, and this is your power, 3x minus 7. So whenever you're solving exponential equations, the strategy is to get both the left-hand side and the right-hand side to be of the same base. Well, I can rewrite 32 as 2 to the power of 5. Doing so, we get, you'll notice here now we have the left-hand side is 2 to the power of 3x minus 7, and the right-hand side is 2 to the power of 5. Well, the only way the left-hand side and right-hand side can equate is if they have the same number of 2's on each side. So therefore, it must be the case that 3x minus 7 must equal 5, in which case 3x must equal 12, and therefore x is equal to 4. So again, just to reiterate the strategy here, when you're solving exponential equations, the strategy is to get the same base on both the left-hand side and right-hand side. Let's take a look at another example. Now, take a look at the next example here. Again, the same strategy you should always look for. I want to have a common base between these two. This is 3 to the power of x. The problem here is that 20 cannot be written as a power of 3. So when that happens and you don't have the option of equating the bases and then you can equate the exponents, what you do is take the log of both sides of the equation. The base of the log that you take does not matter, so I'm just going to go ahead and write log base 10. So this will be log of 3x is going to equal log acting on 20. Now again, just to remind you, if you don't write the base down, the implied base is 10 here, so I'm assuming base of 10. Again, it doesn't really matter which one you do because what happens is we have the property that this x can now drop down. That was one of our logarithmic properties, so doing so we get. And now you'll notice here I have x times the log of 3 equals the log of 20. So I'm going to go ahead and divide by log of 3, in which case we get x is equal to log of 20 divided by log of 3. And just to show you here, if you would have chosen a different base, let's say we chose a base of 3, we would get the following. And now once again, we can drop down the x. And log base 3 of 3 is actually equal to 1, so that simplifies a bit. But now your answer in this case would be x is equal to log base 3 of 20. So log base 3 of 20 is going to equal log base 10 of 20 divided by log base 10 of 3. All right, let's take a look at another example. In the next example here, we want to solve for x. The problem that we have here is you're going to see that we have an x in both of the exponents here of this exponential. So one strategy when you're in a situation like this is if you notice here we have a positive x and a negative x. If I were to multiply across by e to the x, that would actually cancel off this x in the power of the e here. So first thing I'm going to do is actually multiply across by 2, and we get the following. Now I'm going to go ahead and multiply across by e to the x. Doing so, we get, you'll notice here e to the x times e to the x is e to the 2x. E to the negative x times e to the x simplifies to become 1. And now we're here. Now what I'm going to do is I'm going to bring everything to one side. Now you'll notice here this looks a lot like a quadratic equation. And in this quadratic equation, if we let s equal e to the x, we have s squared minus 2ts plus 1 is 0. Using the quadratic equation we get, so using the quadratic equation here, we get 2t plus or minus. Again, I took the b squared value, so my b value was 2t, so squaring that you get 4t squared minus 4ac. Factored out the 4 and then took the square root of that, giving us our 2, and then simplifying you get t plus or minus the square root of t minus 2. Now again, that's not our answer here. We had let s equal e to the x, so now we have e to the x is going to equal t plus or minus the root of t minus 2. We want to go ahead and solve for x here, so what I'm going to do is I'm going to take the ln of both sides. Now to remind you here, the ln is a log function, and the base it is e. So it's just short form notation. And once again, when you take the ln of both sides, i.e. just to remind you again, I'll put the reminder over here. Ln of x is by definition log base e of x. So when I go ahead and do that, again, I can drop down that x like we've been doing. And this ends up being x ln e is going to equal our right-hand side. And lastly, ln of e is 1, so x is going to equal the ln of t plus or minus the square root of t minus 2. In the next example here, we want to solve the following logarithmic equation. Again, the implied base here is 10, So we have a property that if you add two logarithms with the exact same base, you can change the operation between them to multiplication and just take the log of the whole thing. Doing so, we get. Now we need to solve a single logarithmic equation. Doing so, we go to exponential form and we get. Expand everything out and bring everything to one side and we get. We can factor this doing a simple product sum. This will factor into x plus 5 times x minus 2. And the two values of x we get are 2 and negative 5. Now notice here your logarithmic function, in this case a base of 10, the log function has a domain that is greater than 0. So you'll notice here if I input a negative 5 into my original equation, we would be taking the log of a negative number. Therefore negative 5 is inadmissible. Letting x be 2 satisfies both of these logarithms. The logarithm on the input will be greater than 0. So the answer to this logarithmic equation is x is equal to 2. Let's take a look at another example. In the next example here, same idea. We're subtracting two logarithms, and those logarithms have a base of 3 this time. Because the base is the same, we can write this as a single logarithm through division, and this becomes. Now we can change this to exponential form, getting. And anytime you want to solve a rational equation here, what you want to go ahead and do is you want to multiply across by your denominator. So this time here, I'm going to multiply across by x minus 4, and we get. And notice here, the 3 squared is 9. I'm going to go ahead and expand everything out and solve for x, giving us. So going ahead and distributing the 9 and solving for x here, we get x equals to 5. Now again, I have to make sure that the function is defined in my original equation. So with x is equal to 5, if I sub a 5 into here or a 5 into here, you'll notice the logarithm is defined, it's greater than 0. And therefore our answer to this logarithmic equation is x is equal to 5. Let's take a look at another example. In the next example here, what we have is a logarithmic function composed on itself twice. So this is log base 10 acting on log base 10 of x equaling 2. So what you do here is, first of all, we're going to go to exponential form. So it might help you to actually write the base out explicitly as 10. And going to exponential form, it's going to be 10 to the power of 2 is going to equal my input. So in this case here, 10 squared is going to equal log of x, in which case 100 is going to equal log of x. And again, it might be helpful to write that base of 10 down and go to exponential form again. So this will be 10 to the power of 100 will equal x. And therefore x is equal to 10 to the power of 100. Let's take a look at another example. In the next example here, we want to solve an exponential equation. And like we were talking about before, when you're solving exponential equations, what you want to do is you want to get the same base on both the left and right hand side. So you'll notice here I can take 1 over 8 and I can write that as 2 to the power of negative 3. And now what we have here is 2 to the power of x squared plus 4x is equal to 2 to the power of negative 3. Since the number of 2's on the left and right hand side must equate, we can equate the exponents, giving us. Bringing everything to one side and factoring, we get. And solving, we get x is negative 1 and negative 3. Now notice here, we don't have to worry about values that are undefined for exponential. The domain of any exponential function is all real numbers. So both negative 1 and negative 3 are admissible. So the answer to this exponential equation is x is equal to negative 1 or negative 3. Let's take a look at another example. In the next example here, we're solving an exponential equation. So you'll see here I have an x plus 2 as an exponent and an x over here as an exponent. Ideally, you'd like to get the 49 to the power of x together. Making the first observation, we have the following. And you'll notice here what I did was using my exponential rules, I rewrote 49 to the power of x plus 2 as 49 to the x times 49 to the power of 2. So doing so then, by also bringing the 49 to the power of x over to the other side of the equation, I can now factor out that 49 to the power of x, giving us, if you calculate 49 squared and subtract 1, you end up getting 2400. Dividing across by 2400, we get, simplifying the right-hand side, we get 257 over 120. Again, we want to solve the right-hand side, so I'm going to go ahead and take the log of both sides. Again, the base that you use does not matter. I'm going to take log base 10. Doing so, we get. Take the power of x and drop it down, and then we can go ahead and divide across by log of 49, and we get x is equal to log base 10 of 257 over 120 divided by log base 10 of 49. And therefore, the value of x that satisfies this equation here is log of 257 over 120 divided by log of 49. All right, that concludes today's lesson on solving logarithmic and exponential equations. Thank you.